talks a little bit. Peter said, I have to come and talk about, the big questions in liquid crystals. And so I haven't actually been publishing in liquid crystals for the last couple of years. But after hearing all the talks that we've had here so far, I think that, a little bit of review of the physics point of view as opposed to the more mathematical point of view on some of these issues about dynamics and so forth is appropriate. So I'm going to talk about two things that liquid crystals have brought us, and that they've had an impact beyond the liquid crystal community itself. I mean, of course, the first thing that the liquid crystals gave us, and the most obvious, is all of these mesophases that nobody thought existed. When we were in grade school, we were taught there are 3 phases of matter, and I guess if you were lucky, there's a 4th phase of matter. Does everybody know what the 4th phase of matter is? Plasmas, yes. So there is a PR job that is just unbelievable, right? It's one of these, but they managed to carve out a separate area for themselves by calling it a different phase. So anyhow, really the most spectacular thing, who would have guessed that there were all of these phases? And they're phases that require a different language to describe from what you see in a traditional solid state book, or a book on liquids. You really need to modify a little bit. And I think, in a sense, that's the biggest impact that liquid crystals have had on the scientific world, as opposed to the technological world, is providing new phases and a new language to describe them. So I'm going to talk a little bit about what I call phase elasticity, or phase solids. In other words, these are solids that we describe not so much by the positions of the atoms, but by the Fourier transforms, the Bragg peaks, and the density waves they form. And this really is a better description for the sort of systems that we have in liquid crystals, like a blue phase, where you can't really identify a given particle with a given site. The particles just move all over the place, but they maintain a structure. And then I'm going to talk about dynamics and put it a little bit in the context of the hydrodynamical models and theories that were developed for spin systems and other systems in physics. So just to remind you, this is the part of the menagerie of phases. You all remember what they are. I want to focus, bring your attention, of course, to the cholesteric phase, and you can have a debate as to whether or not you want to call that a liquid crystal. We call it a liquid crystal, but it is really a crystal, right? It is a crystal that has Bragg peaks, it has facets. The only thing that distinguishes it from what we normally think of as crystals is that the particles, the diffusion of the particles is much, much faster. And of course, there are many more atoms per unit cell, even more than the ones that Sharon just talked about. So what you want to be able to do is develop a way of describing the dynamics of these systems that don't rely upon perturbing away from the ground state, which is a periodic structure where you can specify the atoms. So that brings us, if you pick up any solid state textbook, you see pictures like this. You're told that a solid is a periodic array, and you say, well, let's study the 1 atom per unit cell. And then they say, well, maybe you can have 3 or 4 atoms per unit cell, and then the phonon structure gets complicated, and you get complicated phonon diagrams, and you get even as far as the Frank-Caspar phases that Sharon talked about. But at some point, you stop making bigger and bigger unit cells. The other thing that a crystal does is it resists shear and compression. So it has an elasticity defined by the, or described by the elastic moduli. So, and just to remind you how you would describe a system that has atoms that are in a given position, or a piece of rubber, or something where you have locked in the topology or the neighbor structure. So this goes all the way back to the 19th century. You imagine you have, this is a pointer. Here we go. The top one is the pointer. It went off, I see. So which one do I press? I press this guy? The blue one. There we go. Okay. So you have some structure that is, we call the reference space, and which is the ground state of the system. And in the continuum limit, you can't see the atoms, so you just characterize the original state by a set of points x, which live either in a two-dimensional or three-dimensional space in the worlds we're talking about. And when you distort it, you map that shape to something else. So you take x to a new position, r of x, and there's no energy cost to rotating these. So the energy has to depend upon the gradient of this guy relative to that. And we usually describe the energies in terms of the strain, which basically is the difference of the metric tensor formed from this R relative to the unit metric tensor, which comes from the reference state. And when you do that, you get the Lagrangian strain, which has this nonlinear structure. If you look in the solid state books, of course, you never have large strains, so you throw away that and you have the symmetrized strain. But really to describe the full rotational invariance, you need this guy. And I just want to point out one thing right now. So you have a couple of indices I and j. These are derivatives with respect to x. That's, in other words, with respect to this reference frame. So this guy is a tensor with respect to this space. But in terms of this R, it's actually rotationally invariant. So this thing has the property that if you stretch and rotate, you don't change the strain. And of course, that's a very nice thing to have for a physicist because you don't want to have to worry about the fact that this guy might be different from that, just because they're not. Now, sometimes we use the Eulerian strain, which is all you do is you replace x by r of x, and you express these derivatives in terms of derivatives with respect to the place that it is after it's been strained. And this, of course, now is a tensor with respect to the space we live in, which is these r's. But it's still based upon the fact that you have a set of points here whose coordination does not change. In other words, its neighbors don't change as you stretch it around, and there's a minus sign there. Now, the reason why I go through this is because most of you probably remember this as the strain, or the way you describe the strain of a solid. But when we go to phase solids, it'll look a little different. So I was running out of pictures here. Let's go to the smectic liquid crystal. So this was the first phase that people looked at beyond the pneumatic phase, and it begins to have a structure that we associate with a solid. It's a periodic structure. This happens to be a figure I had in my contacts, so ignore the DNAs that are coming out here. So you can think of a lipid bilayer and just think of water in the middle. So if you look at this structure, you say, I've got a layer here, I've got a layer here, and I can think of describing this system by telling you what the position of the nth layer is as a function of a coordinate x, y in the plane. So here, this n labels the layer number, just like the x in the Lagrangian description labels a particular mass point that doesn't change. So if you go and look at the original de Gennes description of the smectic elasticity, and you can even find this in his original book on page 288, his description of the smectic was in this Lagrangian language where he started with a un of xy, and then he said, well, let's just make this a continuous variable and make it z. So his original idea was to describe the smectic in terms of what I would call the natural Lagrangian coordinate. And as we'll see, we usually don't do that now, though it's still, if I have this lamellar system where there's not too much exchange of mass between the different lamellae, this is actually a pretty good way of proceeding. And there have been times when we've done that. The net result is that you have an energy which says that if you compress the layers, that costs you energy, so you have a grad z u squared term. But if you rotate all of the layers, then you don't change the energy, and that's why you only have a grad perp squared here instead of a grad perp term. And this is not the linearized form. This is the form that is, this is the linearized form. It's not nonlinear. So at that point, we don't see a great change between liquid crystals and the rest of the world. But then de Gennes, of course, you can't give a talk about liquid crystals without mentioning him at some point. He had this famous paper where he established the analogy between a superconductor and a liquid crystal. And the idea is that you take the smectic and you look at its mass density or its number density, and you expand it in a Fourier series in the repeat distance of the layers. So we have the average density, which can depend on x, but as long as it's not too rapid. And then you have the mass density amplitude psi, times the e to the I q naught, n being the director, dot x. And of course, de Gennes observed that this psi is a complex number, and if you write down the energy of the system in terms of psi, it looks like a superconductor. But for our purposes right now, I'm more interested in the ordered phase. I take this psi of x, and it has a phase, minus I q naught u, and u tells me where the, the equivalent sets of zero of this factor is, or it basically tells you where I'm going to start the origin. So I can rewrite this in terms of a psi and an e to the I phi, where I've incorporated the q naught x into it. And then I ask, what kind of an energy am I going to have? And the energy that comes from the de Gennes theory is basically grad phi squared minus q naught squared, saying that the gradient of this phase wants to have a value, a magnitude that's q naught. And then you set phi equal to q naught n dot x minus u, and you fix the direction n to be along z, and you just re-express this in terms of that, and you get this uzz. It's the zz component of a nonlinear strain. And notice now that I've got a minus sign here instead of a plus sign, but I have a gradient squared, which looks a little bit like the Lagrangian. And this, of course, is the part that guarantees me that I'm rotationally invariant, because this, after all, the original energy was rotationally invariant. So when I go and express it in terms of the variables that identify more easily the displacement of the layers, I have to retain that. So at this point, you're not really sure whether this is maybe a representation of the strain in terms of the Eulerian variable, because after all, these are derivatives with respect to space. So now what we're seeing is something, the beginnings of a difference between the standard Lagrangian description and the description of phase. Here, this phase u is a function. It's a field in space. It's a function of the position in space. It's not a function of a position in the reference space. And there are all kinds of advantages to doing that. Then I don't have to know what my reference space is, exactly where the atoms are, in order to do it. I can do measurements in the real space, but I still have to tell you, because I've got an anisotropic system where there's a direction of the layers picked out, I have to tell you what that is. And here the way I do that is to say I'm going to pick out a particular direction of n, and then I'm going to compare everything to that later on. Okay. So this was the early 70s. I think it was 72, 70, 71, something like that, that de Gennes first is. Now, it was not done in an empty space. There were lots of other fields of physics that were looking at density waves at the time. So it goes back to Froelich in 1954, looked at a model for a superconductor which involved a charge density wave in one dimension, and he showed that that model had a lot of properties that looked sort of like a superconductor. But if you look at these early papers, and Lee Rice, there's a lot of activity just about the same time as the smectics about, is it possible to make a superconductor by creating a mass density wave instead of looking at the standard superconducting order parameter. And it wasn't until 76 that you saw the process of cleanly saying, look, I'm going to look at the phase of the mass density wave and create a long wavelength theory for it in which I have a gradient of that phase, which is like the gradient of the displacement. So I think, and this is, those of you who want to do history, I haven't yet tracked down completely what the origin is, but I would attribute the idea of looking at the phase of the mass density wave as describing the elasticity to de Gennes. You might say it goes back to Landau, because Landau, wrote down his mean field theories in terms of the irreducible representations and so forth. But none of those papers that I could find go to the next step and say, okay, now that I've got my density wave solid, how do I describe the elasticity? So I would like to assign that to de Gennes. And if anybody knows otherwise, tell me. At the same time, there were spin density waves going on. Overhauser in 1960 was looking at the simple problem of what kind of structures can you have in an electron gas. And he found that you could have a spin density wave where the spins in the electron gas would rotate in a helical fashion. And there was many debates about whether that's true, but this still remains true. So a spin density wave is just a continuous rotation of the spins, and it shares a lot in common with the liquid crystals. So let's go and take this idea of a phase crystal now. I'm not going to restrict myself to a smectic. I'm going to look at the sort of crystal structures that Sharon talked about. I have a periodic lattice described by a set of reciprocal lattice vectors, rho g. So I can expand the density. So we're used to saying that rho of x is equal to rho naught plus some rho g e to the ig dot x, summing over all of the reciprocal lattice vectors. And usually, you don't let that guy depend on x when you're describing, say, the X-ray structure and so forth. But we can do exactly as we did in the smectic. We can say that this rho g has a magnitude. It has a phase, which is determined energetically. And then it has something that tells you about the displacement of the thing. So there's an e to the ig dot u. And this u is, it is the analog of a displacement variable. But again, this is a field in space. It's not a field that tells me which particle is moving. And I can define a variable that looks very much like the one I described for the Lagrangian elasticity, x, now minus u of x, because I want the u to tell me where the 0 is. So remember, when I put this all together, I get a g x minus u. So if I change u, all I'm doing is telling you where the 0 of my things are. And I can define a deformation tensor, which is the derivative of the alpha component of r with respect to I. Now, I'm doing something here where alpha is going to indicate this displacement variable. So this will have the number of independent components that I have for g. So if I'm talking about a one-dimensional system, the smectic, then alpha has only one direction. See? If I'm talking about a two-dimensional system, a discotic, then I have an x and a y here. And if I'm talking about a three-dimensional system, alpha will run over all three of them. So this looks a little bit like what the Lagrangian elasticity people would call the deformation tensor, but it's not with respect to the position of the particle relative to its position at some reference state. It's defined exactly by this. So I can define that the analog of that nonlinear strain that we got out of the de Gennes smectic model is a u alpha beta, which has the number of indices as r, delta alpha beta minus lambda lambda transpose, and it looks like this. So this is the correct nonlinear strain for a phase crystal, and I'll point out to you some differences. So this alpha beta is the index that goes with r. It's not an index that goes with the position in space. So this is a tensor that rotates with respect to this group, or equivalently to what the g is. Yes?
Properties of the nonlinear term with the linear part? It's because
scaling part. This term here is required to make the system. This strain is invariant with respect to rotations. Okay, so it's exactly the same thing. I started off with the grad phi squared. That if I rotate the direction of grad phi, I don't change the energy. And this is the same thing that comes back. So if it says that if I take the crystal structure that I've imposed upon the fluid and rotate it rigidly, I don't change the energy. And this is set up so this guy does not change if I rotate the system. Okay. So it's not, I don't know quite what you mean by scaling properties.
Because I'm trying to connect it with differential geometry. I see the strain, the first two terms is related to deformation.
These two.
Geometric.
These two are equivalent. That's
No, do you mean that usually it's the lead derivative?
Yeah.
Yeah, but it's not right.
It's not right. Yeah. Okay. So if I can write down a phase model, and I understand we're going to hear something about the Hohenberg Swift model for rolls in heated systems, and so you get an energy that is constant on a spherical curve, and you just write down the phase for that, and you can then find a phase that has a set of rho g's. And you can then expand the free energy in terms of these nonlinear strains that preserve the rotational invariance after I've stretched the thing. And you basically get something that looks like this. Now, most physicists, if you ask them, if I give you the free energy as a function of the strain, will tell you that the stress tensor is the derivative of the free energy with respect to the strain. That's not true. The engineers are more careful about this, I've found. So this guy is a tensor with respect to these alpha beta variables. The Cauchy stress tensor that we always talk about, and the one that we know has to be symmetric in the end, is a function of, is a tensor in the space we live in. In other words, the x's. So this guy doesn't have the right rotation properties at all. And you can show that, in fact, the correct Cauchy stress tensor is this guy. Now, if I look at the linearized form, this guy has a delta function and a delta function in it, so I can toss out the, if I expand this out, it has a delta plus a grad u. So if I look at the linearized form, then in fact I can throw these away and just use a linearized that, which is what you see in most solid state textbooks, because most solids don't stretch enough that you have to worry about the nonlinear form. So there are lots of advantages to this. The displacement field is a function of a point in space rather than some reference point. It makes the theory of topological defects, at least in my mind, a lot easier to think about. Because remember that the phase here, if I let u go to u plus a Burgers vector, I don't change anything. So if I define some circuit where u goes around and changes by a unit vector, a Burgers vector in space, I've got the equivalent of a topological defect. So it puts it in a footing that looks a lot more like what the various models that particle physicists and others like to talk about are superfluid helium, where you have the phase of the condensate wave function. If you make it go around by 2 pi, you've got a vortex. Just to show you what you can do, now that Mathematica and things like that are around, you just toss in the equation rho of x equals sum over g cos g dot x, and ask for the, what do they call this? The density function of that. So this is a hexagonal crystal, which was just constructed from there. And then I just put in u of x does this, and here we get a dislocation. Now, I'm not quite sure why this isn't quite as symmetric as I'd like, but you can see here the 2 extra planes that have been inserted that came out from just looking at the phase variable. So there are advantages of that. One of the places where we found this very useful was in quasicrystals. So we've heard what a quasicrystal is from Sharon. Here's an example of the pentagonal quasicrystal. So what do you have? You have something that has a 5-fold symmetry. So this reciprocal lattice requires 4 independent reciprocal lattice vectors to create the lattice. And so you expand rho g into e to the ig dot x. And you find now that you have, since there are, I should have drawn a picture here, but imagine that you have 10 spots in a circle that run around. And with each one of those, I'm going to assign a phase that goes with that particular g. So I need, if in the circle I have 5 different phases, and there's a constraint on the sum of them because I can add 5 of the vectors together to get 0. And then I have 4 independent phases that can be changed at will as long as they're done uniformly. And they will give us a displacement of the lattice that costs 0 energy. So there's the usual displacement variable, g dot u, which tells me about the displacement of the lattice. And then there's another representation of those 4 things, which I won't go into the details about, but since I need 4 variables, there's something here called a phazon variable. If I displace this guy uniformly, I rearrange the atoms, but I don't change the energy. So this now gives us an easy way of describing the continuous distortions of a quasicrystal, which is much harder to think about when you're trying to think of, I've started with a set of tiles, and I'm going to let them obey the Penrose rules and all of that. So here is a quasicrystal generated by taking sum over g for 5 g's around a ring of cosine. And you can see it has the sort of pattern that you would expect. And this shows what happens if I let this phase, it actually has to be in a 4-dimensional space. It's complicated now, but it's basically there exists a Burgers vector, and I allow the Burgers vector to make a circuit, and you convert that into that. And if you look carefully, you can see what it is. So here I would say that I participated in this, and I know that the work that we did on this was influenced by what we learned from de Gennes in smectics, the idea that you describe a phase solid. This is actually becoming a field now that's really getting a lot of traction. So just to give you an example, there's this wonderful set of papers by Alain Kerma where he's describing the formation of crystals by using these phase solid methods. So he starts off with a model, which basically is, you take a model of the fluid phase, which is orientationally invariant. You take the simplest form you can, and then you set it up so that when you cool it down, it wants to form a BCC lattice, right? And so now you have a field in space everywhere that will describe a crystal for you when you go into the ordered phase. So he starts off with little clusters, and he looks at, in this particular case, the formation of a polycrystalline solid where you have these grain boundaries. And so this is a simulation that is not done by taking little atoms. It's a simulation that's done by finding what the minimum energy of a free energy that's defined everywhere in space. And I'm told that this really is more efficient than trying to take 100,000 atoms and let them move around. And you get the same information.
Something called phase field crystal. So they insert another word. It's not a phase crystal, the phase field crystal. And there are lots of simulation pictures that look just like that.
Yeah, I suspect it. I think its origin is the same, right? So I mean, I just picked out one. The other thing is that there was a reformulation of crystallographic space groups and how you describe them by David Mermin in response to quasi-crystals, based entirely on the phase crystal language, because you really have great difficulty classifying the quasi-crystalline states using that. So I would like to say that this is a direct line, at least, from crystals. Okay, now I'd like to switch for the second half of the talk. We've heard a lot of talk about dynamics and the Leslie Erickson equation. So I'd like to talk a little bit about putting those into the context of the broader picture of how physicists thought about it. So our first hydrodynamics goes back to, hydrodynamics means water, right? The dynamics of water. And it goes back to the 19th century. And it's basically, it's a mechanical, the original ideas were basically mechanical. You take Newton's laws and you apply it to a fluid, to a continuum. So in the beginning, you didn't see free energies in there at all. You just saw, I know what a mechanical pressure is, I know what a force, I know what an acceleration is. But there was the famous mistake that everybody likes to point out that Newton made. He got the sound velocity wrong because he had the isothermal instead of the isentropic sound velocity. And that, that came because you didn't have the full, thermodynamics correctly employed. Excuse me?
Look what it got him.
Look at what it got him. Yes, look at what it got him. There we go. Not because of that. Not because of that. Let's not call it a mistake. Let's call it an oversight. So, there was developments later on, and eventually there are alternative derivations, not based upon mechanics so much as the existence of conservation laws coupled with the thermodynamics. Now, I don't know exactly at what point in history that took place, and I can't point it out, but by the time I was in school, that was the preferred derivation for at least some class of physicists as opposed to the, fluid mechanics. Now, there's a real landmark here in 41. I mean, so superfluidity had been discovered, in 1911, I guess it was, and people found all these unusual properties, superfluid flow and so forth, and they knew that it had to do with the development of a coherent quantum mechanical order, and you like to think of the state as having a condensate wave function that has a phase, and we all know that a quantum mechanical wave function, the gradient of its phase is the momentum. So there was an extra source of flow, and Landau figured out how to generalize these equations to include the effect of the superfluid flow coming from the gradient of that wave function. So in a real sense, what he's done is he's taken the Navier-Stokes and augmented it by a broken symmetry variable that happens to carry that. Now, in this sense, it was a natural to do hydrodynamics because you already you knew that you had some flow in the problem. So you wanted to find a way of keeping track all of the flow, the normal flow and the superconducting flow. But it was not identified so much as being a generic broken symmetry system. So, and then, in 68, we had these Leslie Erickson theories, which came from a community completely foreign to the community that looked at this. I don't think there was other than de Gennes, who finally was doing liquid crystals in the late 60s at Orsay, managed to find this, but you could not have found a card-carrying physicist who knew about these. And this was, again, a theory that in my mind really goes back to the sort of mechanical theories of Navier and Stokes. All they did was to add a unit vector field and ask how does the dynamics change. And out came a theory which really is a broken symmetry theory, and I'll have some words about whether or not it's hydrodynamic or not in the original formulation, but certainly in the low frequency limit, it gives you a hydrodynamic thing. And what caught the attention of the physics community was this 1968, I don't think this has ever been done before or since, a paper written by the Orsay liquid crystal group. Can you imagine today writing a paper where you say you're a part of a group and you don't get a citation for it?
The Higgs.
The Higgs. The Higgs is a group. Is it the Higgs group? But there's somewhere there are the names of everyone. Here the names weren't there. He calculated the normal modes of the Leslie-Erickson equation. That tends to be what physicists do, is to ask what the normal modes are, and there were extra modes. So parallel to that, there were other developments. So in the 30s, Felix Bloch said, let's look at the excitations of spins that have been aligned because of an exchange, and you have these magnons or spin waves which have a dispersion relation in which the frequency goes to 0 with a wave number. In 1930, Louis Néel invented antiferromagnetism, and you can do the same thing. There are antiferromagnetic magnons which have the property that omega goes to 0 with a wave number. So in the 60s, people began to realize, and there's a number of names that played around with it, that look, if I have a field, a system in which the frequency goes to 0 with Q, then should I not have a hydrodynamic regime? Now, I should have written these things a little better. But remember that hydrodynamics is the dynamics, now that we say it, about thermal equilibrium. And so it's a slow process. It's the omega tau much less than 1, where tau is some characteristic collision time and omega is the frequency. The calculations of these spin waves, were excitations from the ground state, and there's no damping at all. So they really are in the opposite limit, that omega tau is much, much greater than 1. And since most of the time the magnets existed at low temperatures, you didn't necessarily worry about the hydrodynamic limit. So in '69, so notice this is just about the same time that de Gennes was working on the liquid crystals, and it's coincident with the Leslie-Erickson. Halperin and Hohenberg developed the definitive formulation of the hydrodynamics of broken symmetry systems. And what came out of this is that you can identify those variables which have frequencies that are guaranteed to be less than the inverse collision time, and they're guaranteed to be that by having dispersions where the frequency goes to 0 with the wave number. So if you make the wave number small enough, you're guaranteed to have an omega which is much less than tau. And there are two types of variables. There are conservation laws. I should have written it here. So if I have d rho dt plus grad j equals 0, and I take the Fourier transform, I have omega has to go to 0 with q. And then there are the broken symmetry variables. The broken symmetry variables say, look, if I have a state that it's originally I have some isotropic space and I order spontaneously along some direction, then I can rotate the thing arbitrarily, rigidly, and I don't change the energy. But if I have a little bit of a wiggle, I don't, and I will get some things. So in '72, which was largely as a result of being confused about Leslie-Erickson, there's this famous paper, actually my name is on it, deriving the hydrodynamics of liquid crystals using the spirit of Halperin and Hohenberg. And this, whereas the original Leslie-Erickson formulation was not fully hydrodynamic in that there was one mode that decayed to 0 fast, this theory was based upon identifying from the beginning what the conserved variables were. And at some point, and I must say, I'm sorry I didn't talk to Pierre Gilles about it at the time, if you look in his book, he has a formulation of Leslie and Erickson which is not the same as Leslie and Erickson. And de Gennes would never have said, look, I've done it differently. He gives full credit to Leslie and Erickson. But his formulation, which is basically their way of doing it, doesn't have the extra fast mode. And again, I should have written the equations down. The difference is that Leslie and Erickson assigned a kinetic energy to the director, and de Gennes said, no, all of the kinetic energy is in the velocity, which is really what we did. So again, to emphasize, hydrodynamics is long wavelength, q lambda less than 1, omega tau much less than 1. The variables that give you hydrodynamics are conserved variables and broken symmetry ones. So you could outline a program where all you want to do is talk about hydrodynamics. But really, a lot of the time, we're interested in order parameters and things like that that are not hydrodynamic. They decay in a microscopic time. So it's interesting to have phenomenological equations that capture the correct symmetry, even for those variables which are not conserved or the broken symmetry ones. And so I will run through here in the 10 minutes that remain sort of how we think about it. So let me look at as I say, the variables are conserved variables. So there's some variable phi and a current associated with it. If I Fourier transform this, I get an omega and a q. So omega is going to go to 0 with q for conserved variables. The broken symmetry variables, there's a free energy whose energy goes like the gradient of phi squared and not phi itself. And dynamics really, and in the end, all of the dynamics we have to worry about, other than subtleties about entropy and so forth, is contained in the harmonic oscillator. You have variables which have a specific sign under time reversal. So x is even under time reversal, p is odd under time reversal. There are reactive or just purely mechanical couplings between the fields which have opposite signs under time reversal. So p dot is the Poisson bracket of p with x times the derivative of the Hamiltonian with respect to x, and vice versa. Right? And then you can introduce dissipation if you want. These things have to do with phenomenological statements of how you decay to a ground state. In this case, you're putting an artificial friction back in. And once you have these equations, you can calculate the mode structure. So in essence, that's how we're going to go about deriving the equation. So let me take the simplest example I can think of. This is closely analogous to spin waves, to spin systems. I'm just going to put rigid rods on a lattice and put them on frictionless bearings, and allow them to interact so that at low temperature they want to go to a phase that's ordered, a dramatic phase. Here, the guys are spinning. So there's one conserved variable in the problem. It's the angular momentum. And the only angular momentum is the spinning of these guys. So I have an equation here, which is a conservation law. And in the disordered phase, I can write down a phenomenological, since this is conserved, I write down this current that goes as the gradient of the derivative of the free energy with respect to L. And since L, the angular momentum, is the moment of inertia times a spin, this is the spin frequency, and I get an equation, a diffusion equation for the spin frequency. Right? And so the energy is an L squared over 2I plus an F of theta. Now I go to the ordered phase. Well, I've now got the rods are pointing in one direction. I have a director n, so I have the kinetic energy part, and I have the energy that comes from the gradient of the director. So now I can look at the equation of motion for n. There's a Poisson bracket that couples n to L. N is even, L is odd. And then there's a dissipative term that says that this thing is going to, this is what ensures that if I'm out of equilibrium, I decay towards the equilibrium state. And notice now that once I've got a coupling between n and L, I have to have a coupling between L and n, because those are, and these, I'm writing in a Poisson bracket term. You could also say that what I have are reactive terms that couple n of one sign to L of the opposite sign. And once I've got one coupling, I have the other. And so I still have the diffusion here, and this defines the complete set of equations. Now, how much did I do this or not here? Right. So now let's look at what those equations say. The Poisson bracket says that n rotates with the frequency that's determined by the L. And the h here is exactly the Frank h. It's delta h delta n, so it's k del squared n. And we put all this together. Wait a minute. Did I get this out of order? I think I'm. This got placed. I was fiddling things around. This goes with another slide later on. But anyhow, this model has a spin wave. If I turn off the damping, this nu. If I turn off the damping, I have omega xy goes as CQ, and the C is the Frank elastic constant divided by I to the 1/2. Oh, I see. That should not be 1/2. This is C squared. And if I put in the damping, I get this. And notice that it should be pointed out that these equations, which have damping in them, have an overdamped regime, so that if I make the damping large enough, I go over into a regime which is still hydrodynamic, where the propagating mode has become diffusive. And then there's still, I still have the conserved spin diffusion for rotation perpendicular to the sample. Okay. Now, I can add friction. So suppose I took this whole thing and put it on a substrate that says the thing wants to slow down. So here, this just says that the omegas want to decay to 0. I add those. So now I've lost the conservation law for the angular momentum, but I haven't lost the broken symmetry. And so we still have a hydrodynamic mode, which is purely diffusive now. It's no longer a propagating mode, but it goes to 0 with q squared. And then I have two fast modes, which are telling me that the angular momentum is decaying to 0 because I put it in contact with a substrate that absorbs the angular momentum. So if I were to do a purely hydrodynamic theory, I would want to get rid of the omega and just keep the n right here. Okay, so that's a beginning. So that's the first way to think about a broken symmetry of the type that Leslie and Erickson have. So then we go to Navier-Stokes. We have a free energy. There's a kinetic energy. So g is the momentum density. G is rho, the density, times the velocity. And I want to write it as because g is the one which I can write down in microscopic form for, and it's easier to derive Poisson brackets with g rather than v. And then there's the free energy that depends on rho. So you have a conservation law for rho, 3 conservation laws for the momentum, and a conservation law for the energy. And so applying the sort of things I just discussed, you can turn, these are basically the Navier-Stokes equation. There are 2 longitudinal sound modes, 2 transverse diffusion modes, and 1 heat diffusion mode to give you all 5 modes associated with the 5 conserved variables. So let's talk about a solid now. So the solid we're talking about are these phase solids, where in addition to the density, we have a mass density, and there's an energy that's associated with the strain variable. There is the momentum is still conserved, so there's a density still conserved. There's a momentum density. I then have an equation for these new fields u alpha. So there's a commutator of u with g, and it gives me exactly the lambda alpha I had before. So this is delta alpha I plus grad u grad alpha. So the du dt has a reactive term that's linear in the velocity and a dissipative term. Have I turned it off here or something? Or I've killed the battery. Well, okay, so there's a dissipative term. Now, once I've got a coupling between u and v, I have to have a coupling between v and u. And that looks like this. So you're used to seeing the gdt as the force df du. Yes.
There's a stick there.
There's a stick. Oh, this is even better. When you give talks about liquid crystals, it's always great to have sticks because, you're doing this. And then, of course, if he's asleep, I can. Anyhow, so, this guy, once you have this guy, you have to have this one. This looks like the force equation. But remember that this should have been an alpha here. I didn't change that quickly. So remember that the I and the alpha live in different spaces. So in fact, the Poisson brackets do the thing to convert the alpha variable here to the I. We have the pressure, we have the viscosity, and we put all those together, and we've got oh, I'm sorry. Did these things get out of order? Well, yeah, so this gives you that, then you want to count all the modes. This is a crystal. So we have 5 conservation laws and 3 broken symmetries if it's 3 dimensions, 2 broken symmetries if it's 2, and 1 if it's 1. And so what are the modes? So let's just think of the 3 dimensions. We have 2 transverse phonons with a plus and minus direction. That gives you 4. 1 longitudinal direction, so I have 6. There's a permeation mode. So here, notice that I don't say that u is exactly v, which is what you would do if you said the particles were actually fixed. And there can be a difference between u and v. And that really is telling you that I'm not fixing the number of particles that are in any given unit cell. I can squeeze the unit cell and allow the unit cell to squeeze while the particles just stay fixed with their density. And that means that I have particles flowing in and out, and that's a permeation mode, which if you were to look at a crystal from the standard solid state picture, is a diffusion of an interstitial or a vacancy. But those are always sort of second thoughts. They're not built into it from the beginning, whereas here it's a necessary part. And if you're going to describe the hydrodynamics of the blue phase, you need this. So you can think of other things. If I do a tethered solid now, where I lock the solid together, then I want to go back to a more Lagrangian picture. And you just put du dt equal to that, and I can go, and the tethered solid is going to lock the density. It's going to get rid of permeation and density, interstitial diffusion, and you get the standard model of a crystal, of a Lagrangian solid. You can put a Lagrangian solid in a fluid, and then you have the displacement of the fluid variable, of the solid part, and the fluid velocity itself. And if you move the solid relative to the fluid, there's friction. So you put, and if they move together, there's no friction. So you put in a phenomenological term that looks like this. And then, of course, you have to put the opposite one in, because the total momentum, which is the momentum of the solid plus that, is conserved. And you then get an effective, if you go to long wavelength limit, this thing, even though it's sitting in a fluid, has equations that look very much like the solid. So now let's go to the liquid crystal. It's the same game. The difference is we don't have a rho g here. We have the director. And we have a free energy, the Frank free energy. We have a reactive coupling between N and V. There's a Poisson bracket. So notice this lambda is reactive, a dissipative part. Once this is here, we have to have the equation for G. And lambda has a part. This is basically omega. So we have an omega cross, So this thing combined with the gradient gives me N cross omega. And then there's, because of the way that things are constructed, that there is another term that's symmetric in the variables. This is a reactive coefficient. And we put it all together, and we get this equation. dN dt is omega cross n plus lambda na plus 1 over gamma times h. Notice now that in the n equation, this is the only dissipative coefficient, and I have this new reactive coefficient that's allowed. These equations that we get, though, properly interpreted, are identical to the hydrodynamic form of the Leslie-Erickson equations. So I'm not going as fast as I thought I was going to. Let me say that there's another way you can think about the Leslie-Erickson, and this is something that I was glad to figure out finally, because I was always confused about how the angular momentum came in. Suppose I choose to describe my system in the same way that I was describing the rigid rods. So I have a rigid rod, and I can identify a spin angular momentum with a rigid rod. Then I can divide the system into the center of mass motion. The center of mass momentum is conserved by itself, and that means there's a conservation law for center of mass momentum. And I can split up the energy into a kinetic energy of a center of mass and the rotation about the rods. Now notice, I haven't said anything about n yet. This is the angular momentum of the system. So now we do the same thing. We take the commutator of n with the angular momentum. This is exactly what I had for the rigid rods. But now we have the problem that if I spin the angular momentum, if I start spinning the rod, it's not happy unless it's spinning with the fluid. So if I take the center, if I take all of the rods and I rotate them like that as the center of mass is moving, then there's no motion of the rods relative to each other, and there's no friction. So we introduce friction terms, which are the exact analog of what I did for the solid in the fluid, and you get these things. So now I have, these are real dissipative coefficients. They're dissipating energy if the angular momentum is not following that. And once I've got these, I've got to put in the antisymmetric parts of the stress tensor, and you put all of this together, and you almost have Leslie-Erickson. It looks like this, but there are a few extra terms. We now can keep straight the difference between omega and n. We have an omega, we have a diffusion for parallel direction. And if we take the limit that, let's see now. I've now lost myself a little bit. If we ignore the inertial term, that's right, ignoring the inertial terms, we get this equation, which is, rather we keep the inertial terms, but I forgot now what I set equal to 0. Let me go to the next one here. This is the equations that come out for n from that. You have an inertial term, you have a term that comes from the h dot, and then you have this thing which is identical to Leslie-Erickson. So if I set this side equal to 0, I get the old hydrodynamic equations. But what's happened now is I have extra non-hydrodynamic degrees of freedom, which tell you how the angular momentum decays to the rotation of the director. So, in my mind, that's a cleaner way of thinking about it if you are not going to do pure hydrodynamics. The thing that's a little amazing here is that you can reduce this to the Harvard form, in which this lambda was a reactive variable, and it's the ratio of two dissipative coefficients. And I must say I still don't fully understand that, because they really have different origins, but when you get down, the equations are the same. So you can regain the Harvard from that theory. So everything is there. Okay, I can just say, we can, Mark told you about pneumatic elastomers, so I can use the same sort of theory for pneumatic elastomers. There's a more complicated elastic energy, and we can go through and calculate the effective hydrodynamics, and you get this wonderful mode structure that looks very much like a discotic liquid crystal. You can also take this system. I haven't talked about it here in the meeting in June, I guess it is. We're going to talk about active media. Well, this is set up so that you can add the extra active terms, force dipoles that are driven by motors and things like that. And one of the things you find when you look at the active media is that not only do you have some terms in the stress tensor that are not thermodynamic, but you can see Onsager breakdown. And of course, that is, if you take a mechanical point of view and not a thermodynamic equilibrium point of view, then you have to admit that possibility. And you see it pretty cleanly coming out in models of systems where you have active media running around. So, I guess I'll just amuse you here. So here is a model. Do you know what a rattleback is? This is a Russian rattleback. It has the property that if you spin it in this direction, it will spin happily. If you try to spin it in the opposite direction, it'll stop like that and it'll go backwards. That has to do with chirality. So I had Jerry Golub have an undergraduate make a bunch of chiral Cs, which you can see here, and put them on a vibrating table. So that's vibrating. You can see that this vibrational motion gets converted into a spin. And then you put them together in a gas. And if you look carefully, you can see that the things are moving very slowly around this way. So what we've done is to convert the up and down motion via chirality to spinning the guys that then gave us a net rotation about the center. And, of course, I wouldn't be saying this if you can't write down a theory for it that's along the lines that I just discussed, and the theory does a pretty good job of predicting what's seen. So there are lots of things that can be done, and I see I've gone over my time, and I will stop now.
Thank you, Tom. Perfectly timed.
Good questions. Yes.
I wonder whether your theory also incorporates couple stresses in the couple stresses.
You mean as in angular momentum?
Yeah.
Yeah, it has it. So, if you take the point of view that you're describing a hydrodynamic system, and you say that the momentum is the momentum of all particles, then our old theorems that we've had from our youth, that the stress tensor is symmetric, still apply. Now, the couples that you're talking about come in, they enter the stress tensor in terms that have two, the force equations have two derivatives rather than one derivative. And so even though the derivation tends to look like it has antisymmetric parts in it, I can rearrange it so that the stress tensor is symmetric. So we have all of those antisymmetric couplings and so forth.
But the couple stress is related to the antisymmetric part of the stress,
Yeah.
but it is independent from it.
Well, not, it depends now. It doesn't, if you have a true hydrodynamic system where I've not artificially identified a separate angular momentum for the rods, then though I may have an antisymmetric term, which does in fact naturally come out of the Harvard thing, I can convert it to a symmetric one. When I look at the rods, then I do have to have an antisymmetric part because indeed those things, you know, I have to be able to balance the total angular momentum. So in the model where I had rigid rods, there is the antisymmetric part in the couples. When I look at the pure hydrodynamic form, I can get rid of it.
More questions? I had one, Tom, and that is on that film that you showed on the previous transparency, you're having simple body rotation. I mean, I couldn't tell by...
So what I have here, this is a plot of V of R versus R, and it gets bigger as I go out. So and it's not exactly, so if I had a constant angular velocity, this would be straight. And so it actually is not just that. You know, these equations, which have all of those things in it, when solved, give this curve. And these are it's very hard to do these measurements in the undergraduate data time. So you certainly get the velocity getting larger. So there's some subtleties about the boundary condition. It turns out that the boundary, usually we're used to thinking of the boundary condition is that the velocity at the interface is equal to 0, right? That's certainly not the case here. And so there is a boundary condition that has to do with penetration depth and so forth.
Right. So that the omega, the capital omega there is...
It's not a constant.
It's not a constant.
No.
Yeah. Okay.
And maybe just a comment in that direction. Keith Moffat, who's somewhere around, actually, he's got a nice example of this rattleback.
Yeah.
He did actually a dynamical systems model.
Oh yeah,
rattleback. So maybe have you incorporated that into your?
Well, when we looked around at some of that, I actually tortured my graduate student asking him to set up the simulations for it. It's not trivial. It's a messy problem to do right because it's the friction and all of that. But if you go online now, you can find that there are high school students who write code for it and so forth. But originally, the first rattleback I saw, and you probably the rest of it, you go to a typical science museum and you get this piece of plastic that's a little translucent, maybe, and it's flat at the top, and you turn it over in the bottom, and it's sort of curved, and you can't figure out what it is. But what it does is it has a structure on the base that is chiral. So what I like about the Russian rattlebacks is you have these turtles. If you turn the turtles in so the system isn't chiral, it'll spin in both directions. And when you do that, it's become chiral and it'll spin in only one direction.
So there is one sort of possible idea for an experiment, because you can have 3D printers now.
Yes.
Like design the inertia tensor.
Yes.
So you could basically have a parameter space to explore.
Yes, you could. Yeah. Whereas we took the wires and we had an undergraduate who made 500 of them like that.
So they weren't necessarily all the same.
Yes, right.
Any other questions? Well, I'd like to thank you.